So yesterday we left off with conversions, so we need to be able to do those conversions to do empirical molecular formula. So the way that they determine that is they burn them. And then they, of course, in a combustion, what are always the products? Carbon dioxide and water. And then, of course, if there's other things present like nitrogen or something like that, you would get some oxides in there. Like if sulfur was present, you would get sulfur dioxide. If nitrogen, you could get some nitrogen dioxide, and that's how you would know there's other things present besides just carbon, oxygen, and hydrogen. Okay? So I am going to just jump right into the examples because I feel like you learn better by examples than reading the words. But they do theirs a little bit different, so I'm just going to jump to the example. And this is the way I taught you in Chem 1. So there is the actual process. You're going to remember you divide everything to get to number of moles. Smallest number of moles you divide by to get your formula. So let's start with this particular compound. And I'm going to pull up a new page on mine because I write way too big to fit in that little space. So I'm going to give myself a whole blank paper here. So if we have, remember, if you have a percentage of something, what do? I have all these percentages. There's something I assume.
Assume 100 grams.
Assume 100 grams, because if I have 100 grams, that means I have 71.65 grams of chlorine, etc. So we're going to start, and we assume 100 grams. So assume. So if we assume that, that means I have 71.65 grams of chlorine. I have 24.27 grams of carbon, and then I have 4.07 grams of hydrogen. So the first thing I want to do is convert everything to moles. So I'm going to divide by the molar mass of each one of those. The molar mass of chlorine is 35.45. It is not by itself, so it's not diatomic. So we don't double the mass. We only do that when chlorine's by itself. When I do that, I get 2.021 moles of chlorine. Then I do the same thing for carbon. Carbon's molar mass is 12.01. And I get 2.021 moles of carbon. And now hydrogen, 1.01. And that gives me 4.030 moles of hydrogen. Does anybody remember what the next step is? You divide the moles by the smallest number of moles. Okay? So that's 2.021, so we're going to divide everything by 2.021. And that's going to give you basically your ratio of atoms. So that gives me that I have 1 chlorine, 1 carbon, and 2 hydrogen. That gives me 2, 1, 1. So that is my empirical formula. If you had me, you knew that we took empirical formula and we did that, because that's showing that's an empirical formula. I'm not sure if Miss Lawrence showed it that way. An N, and we're going to solve for N because that's how we're going to get to molecular formula. Now on the AP exam you would just say that's my empirical formula, but for us we solve for N and we say it's our molar mass over our empirical mass, because this is also asking us to solve for the molecular formula, because it gives us the molar mass is known to be 98.96. Okay, so your molar mass they have to give you. They do a different type of test to figure out the molar mass. The empirical mass is the mass of your empirical formula. Okay, so they gave us the molar mass was 98, right? Yes. 98.96. We're going to divide that by the empirical mass, which is the mass of this formula. So somebody calculate that for me. 49.48. Or did I? 49.48 is what I have. Okay. So if I divide that, that gives me 2. So now I plug that in there. So what is my molecular formula? Yeah. Usually you put the carbon first, so we're going to reverse that around. And that would be my molecular formula. So if you recall from Chem 1, the difference between your molecular formula and your empirical formula, your molecular formula is what is actually the formula of the compound. Okay? Your empirical is your simplest ratio. Okay? For instance, if I have this formula, let me erase all that. Does everybody have that before I erase it? Is anybody still writing? Raise your hand if you're still writing, and then I'll give it a second. Okay? But if I have C6H6, and I had, which is benzene, and I had C2H2, which is ethine, their empirical formula would be what? CH, because they could be simplified. So if I were to take either one of those compounds, C2H2 or C6H6, and I was to do a combustion analysis, it would give me the same percent composition of carbon to hydrogen, even though they're very different compounds. Okay, so their empirical formula would be CH, because that's the simplest ratio that they would come up with. But their molecular formula would be what their true formula is, because ethine is a triple bonded 2-carbon molecule, whereas benzene is a liquid that behaves completely different. But if I were to do a percent composition or an empirical formula, it would come up the same. So that's the difference between empirical and molecular. So on the worksheet you picked up yesterday at the top, it just gives you a bunch of formulas and it tells you to find the empirical formulas. So if you can divide it evenly, then you can simplify it, then that's the empirical formula. Sometimes the empirical and the molecular formula are the same thing. For instance, CH4, which is methane. I can't simplify that, so that would be its empirical formula, but it would also be its molecular formula as well. Okay? Any questions on that difference between empirical and molecular? Okay? Do I need to, you want me to work another one? Yes. Okay, I can do that. So I want to skip over and do, we're going to do the one, we're going to do exercise 12. We're going to skip, I'll let you go and do 11, but we'll do exercise 12 because it's got a lot of stuff in it. It's caffeine. Yay for caffeine. Okay. So again, I write too big to fit in that little space, so I'm going to give us a new... How about a chalkboard today? Nah. We'll go old school and do a chalkboard. Okay? All right, so this time they're giving us the percent of compounds, percentage of carbon, hydrogen, nitrogen, and oxygen. So we don't have to assume 100 grams. Actually, we do have to assume 100 grams again. I'm sorry. So we assume 100 grams, and when we do that, we know the mass. So let's, everybody get going. We'll do it together. So let's start with carbon. 49.48 grams of carbon. Divide by the molar mass. .15 grams of hydrogen. Is this, I can't even talk today. Is this at least ringing a bell from Chem 1? Yes, we do 1 day for free response and 1 day for multiple choice. Not every single test is like that, but a large portion of them are. And typically we'll take the free response first, the FRQs first. FRQs, free response. So now, after we have everything in moles, what do we do next? Divide by the smallest, which is the 1.03. Usually 3 or 4. Sometimes, I'm not very consistent with that. If it's a decimal, I tend to go more. If it's a whole number, I tend to go less, but sometimes I just keep writing. The further out you go, the less likelihood you are to get a fraction. Because remember, if you get a fraction, you cannot have or a decimal, you can't have 2.5 atoms. So I don't know if you remember, you have to multiply by an integer. I don't think one of our examples does that. If you were in my 2 that were in regular chem, we did not do this. So this is new to you. We didn't do this in Chem 1. So that's 1, that's 2, that's 5, and that's 4. So our empirical formula is C4H5N2O. That looks like an H, not an N. So now to find N, it gave us a molar mass. What was it? 194.24. Just 0.2. We're going to divide by the empirical mass, so add up the mass of that. Empirical mass, just to clarify for anybody that's confused, is the same way you do molar mass. It's just not called molar mass because this isn't the molecular compound, it's the empirical. So we calculate the empirical mass, and you should get about 9711. So that means N is equal to 2. So distribute, and you get your final formula to be C8H10N4O2. And that would be your final answer. Okay? So what the next little section in the notes is balancing equation. Raise your hand if I need to go over how to balance an equation. Okay, I will. I'm just going to make up some equations. I'm not going to walk through that process. I'm just going to make up some equations to balance. Okay? All right. Is anybody still writing this before I move on? No. Okay. Then let's continue forth. All right, I'm just going to make up some equation. How about we have some H2SO4. This is, I'm making it up. Yeah, they're equations. I'm just making some up, and we're going to balance them in practice. See if because most of you will remember how to balance them. You just haven't done it in a while. So let's add some calcium. Let's add some calcium chloride. Yeah, we're just assuming they work. Okay. Actually, that one wouldn't work. Yeah, it would actually would. So that would give me calcium sulfate and HCl. So how would I balance that? 2 what? 2 HCl, and I'm done, right? Is that ringing a bell? Because you have 2 hydrogen here, you needed 2 over there, you had 2 chlorine. Yes. Oh, that's a thing. Yeah. Do you want me to do one with 3 things? Yes, please. Okay. What do I want to do this with? Well, let's do it with, let's keep it interesting. Let's put some, yeah. Okay, let's balance that. If we can balance that, then we're good to go, right? How do I know that it comes 3 things? Because I'm going to tell you, and I'm glad that you had me do 3 things because it brings up this. What you would think, it's a double replacement. What you would think would form would be carbonic acid, right? Because you do outside, inside, right? Did y'all do that? Outside, inside go together? When you're doing a double replacement? However, carbonic acid immediately breaks down upon formation. It's very unstable. So it immediately breaks down into H2O plus CO2. So never, ever write H2CO3 as a product, ever. And when we go over reactions, we'll bring that up again. There's some things that automatically break down, but I will stress that a couple of times because don't ever write H2CO3 as a product because it immediately breaks down into H2O and CO2.
And is that just for carbonic acid?
No, there's two other ones that we'll get to when we get to reactions. But this one came up, so I'll stress it. So how do we balance this? Balance your metal first. It's the easiest thing to balance. Sodium. 3 and 2. What do I need to whoa, hello, come back here.
Right side by 2, left side by 3.
So we're going to need a 3 here and a 2 here. Okay. What else do we need to do? I heard someone say we need a 2 here
Yes.
and then a 3 here.
Yes.
Is everything balanced now?
No, because now there's an oxygen.
CO2.
Okay, now is everything balanced? Double check. You have 2 phosphates on both sides. You have 6 sodium on both sides. You have 6 hydrogen. And you have 3 carbon. And you have 9 water. Do we have 9 water? 6. Not water, oxygens. You have 6 plus 3. So we have 9 water. So we are balanced. So if we did that one, we're pros now, right?
Yeah, I should put on the test.
Okay. To be honest, I'm going to tell you a little secret. To be honest, very rarely we ever have to balance equations on the AP exam. They usually give them to you already balanced. Occasionally you will, but most of the time they already balance them for you. That's like a basic Chem 1 skill. Yes?
Will they tell you if you need to balance it?
If there's integers in front of it already, it's already balanced. They're not going to give you one and say, just kidding, it's not truly balanced. So if you have something and it's already got...
If it's not like balanced, will it say that?
Oh, no, you should. If there's no integers, you should always double check that it's balanced. Yeah. But if they already have it, like if they had presented it to you like this, with the 2 already there, then you would assume it's balanced. Okay? Are we good on balancing? Okay. This is where I'm going to stop because I want to do the example of the combustion analysis. So if you have, is there a blank space on the back of your notes or get out a piece of paper because we're going to do an example. Yeah, there was one on there.